If we are given 3 points on a coordinate plane, so select any 3 points at random, can we write an equation for the quadratic that passes through these 3 points? Given the symmetric nature of the quadratic, there's only one possibility for me to draw a parabola or find a parabola that would pass through these 3 given points. The way we find the quadratic formula responsible for passing through those 3 points is by using our knowledge of a standard form equation for a quadratic, in addition to our knowledge for what the coordinates tell us and how to solve a system of equations. So the best way to learn how to do this is jump right into an example. So let's say I have a quadratic that passes through the points 1, -5, 3, 5, and 4, 16. And we want to figure out what the equation is of the quadratic that passes through these specific points. We have our standard form equation off to the right, and now we want to make sure we can correctly interpret what these coordinates are telling us. When we're dealing with functions and a coordinate related to a specific function, that x coordinate is telling us an input, and the y coordinate is telling us an output for that corresponding input. And knowing that, I can generate some equations based on that. I can say that when we plug in 1 for x in my standard form quadratic, or in the quadratic we're looking for, I should say, we know that the equation should output -5 based on that coordinate. Additionally, the second coordinate is telling us that when you plug in 3 to this quadratic equation we're looking for, we're supposed to get 5. And when we plug in 4, we're supposed to get 16. With the goal of ultimately finding the values of a, b, and c in order to write the quadratic, what we've just done is produce a system of 3 equations with 3 unknown variables. When we clean up this arithmetic, we're going to get a plus b plus c is equal to -5. We're going to get 9a plus 3b plus c is equal to +5. And we're going to get 16a plus 4b plus c is equal to 16. So here is my system of 3 equations. To solve a system of 3 equations with 3 unknown variables, we are going to reduce this system of 3 down to a system of 2. In order to do that, you first select any 2 equations out of that 3 and eliminate a variable of your choice. So let's say I choose equation 1 and equation 2. I can eliminate a variable of my choice. The most efficient and easiest variable to eliminate at this point is c. But to eliminate c, they need to have different signs. They already have the same constant coefficient. So I multiply the top equation by -1 to produce a new set that when I add the equations together, c will eliminate. So with the elimination method to solve systems, to eliminate a variable, you must have the same constant coefficient, but different signs. So c, constant coefficient, currently 1 and -1, so that will eliminate. And we have 8a plus 2b is equal to 10. I now have an equation with 2 unknown variables. In order to solve that, I need another equation with the same 2 variables that would allow me to produce a system of 2 equations. So to get the second equation needed to solve for a or b, I go back to my original 3 equations and I select a new pair. So originally I did 1 and 2 to generate that new equation below. So I can select 2 and 3 or 1 and 3. Let's say I select 1 and 3. So if I write 1 again, in equation 3, when I select my new pairing, it is absolutely critical that we eliminate the same variable as we did with the first pairing. If I eliminate A or B now, I now get an equation with a C in it, but that doesn't help me find the value of A and B based on the original equation that I just produced from the first pairing. So I need another equation in terms of A and B in order to solve the new system. So I must eliminate the same variable as I did with the first pairing. Again, the C values already have the same constant coefficient of 1. But if I added the equations right now, they wouldn't eliminate. So let's multiply the top equation by -1. My new manipulated system will be -A minus B minus C is equal to +5. And 16A plus 4B plus C is equal to 16. When we add these equations, the C's now eliminate, and we have 15A plus 3B is equal to 21. By selecting pairings and eliminating the same variable from the pairings that I select, I have produced two new equations that are responsible for forming a new system of two unknowns. I can solve this system of two equations and two unknowns for either A or B by eliminating the other. So it is your choice at this point if you want to eliminate A or B. Let's say we want to eliminate B to solve for A. Again, we need the same constant coefficient in different signs. So I want to avoid multiplying by fractions. So a shortcut that you can always do, if you're unsure what to multiply each equation by, you can multiply both equations, by the way. It doesn't always just have to be one. You can always multiply the top equation by the constant coefficient in the second, or in the bottom equation, I should say. So I can multiply the top by 3. So again, we're trying to eliminate B here. And I can multiply the bottom by the constant coefficient from the top. So I can multiply it by 2. The only thing you want to consider is that we need them to have different signs. So right now, they were originally both positive, so I'd want to make one of these negative so that they get different signs. But if you're ever unsure of what to multiply the equations by, usually you want to reach a value that is the least common multiple of the current constant coefficients. But in the event that you can't think of the least common multiple, you can always bail yourself out by, again, multiplying the top equation by the constant coefficient from the bottom equation, and the bottom equation by the constant coefficient from the top equation of the variable that you're trying to eliminate. Simplifying this, make sure you're multiplying both equations by that scalar. So we're going to get 24A plus 6B equals 30. So common mistake to forget to multiply that constant on the other side of the equal sign by that scale factor. Then we're going to get minus 30A minus 6B is equal to negative 42. Now when I add these equations, the b's cancel. And I get negative 6a equals negative 12. So a is equal to 2. If I know the value of a, I can now find the value of b by substituting back in to one of the equations that produced the value of a. So I'm plugging back into one of my equations from the system of 2. It does not matter which one we choose. So how about we select the top equation? If I do 8 times 2 by substituting 2 in for a, plus 2b is equal to 10, I'll get 16 plus 2b is equal to 10. We'll get 2b is equal to negative 6, and b is equal to negative 3. Again, I have to substitute that first value that I find for the first variable back into the system of 2, because if I substitute it back into the system of 3 that I started with, well, I don't know the value of c. I only know a, so then I would be left with a system of 2, and it's a wasted effort. So now that I have a and b, Once you have two of the variable values, now you go back to the original system of three, and you choose one of the three equations, substituting in for two of the variables you found in order to find the third. Choose the equation that requires the least amount of effort. So how about we plug into the first equation? I know A was equal to 2. We know B was equal to -3, I believe. Yes. And now we can find C by solving for this. So 2 minus 3 is -1. Add 1. We're going to get C is equal to -4. Let's make sure we finish the problem. So I've solved the system of three for A, B, and C. Don't forget or lose sight of the goal of this question. It was to write a quadratic function that passed through those three coordinates. What we did was we took those three coordinates to produce a system of three equations in three variables. We then solved for the values of A, B, and C. And the reason we want to do that is in order to write a function that is specific to those three coordinates, we need to find the values of A, B, and C, understanding that they just represent constant values in our standard form. Once I have found A, B, and C, I substitute them into the standard form, and the result is the quadratic equation that passes through the three given points. So don't forget to finish off your answer by writing the quadratic function. Don't lose sight of what the ultimate goal is. So that is how you write a quadratic function given that it passes through 3 points.